Hello. So this is a video on the material we covered in last class, and we discussed quantities and units in the last class and unit conversion. So I wanted to go through some simple examples of quantities and units that will be relevant for our discussions, and then that should set you up for the rest of the semester. Okay, so quantities are properties or attributes. They are features that we look out, and when we look out at the world, we find that certain properties or quantities are useful for organizing our thoughts. And so, for example, they could be things like quantities could be length or time. Later on, we'll talk about mass. And there could be some other ones. So quantities are really just, sometimes they're called dimensions, but we don't mean like space and time or X, Y, Z so much. But we really just mean some sort of a property which is useful to characterize the system. So, okay. Now, so we have this idea of a length, fine, but that's not so useful by itself. We have to also supply the concept of a quantity with some sort of prescription for making measurements. So we have to come up with some sort of a way to measure it. And the way that we do all measurements is we come up with some, by convention, we all agree that there's some standardized unit, all right, sort of procedure, really, that we're going to measure things, and then all other scenarios can be compared to that standard procedure. So, for example, meters are going to be a way to measure lengths. So what we've done, now, it's slightly, the way a meter is defined is a little bit different than just a stick. It's a little more complicated, but it's equivalent to this. And so we can imagine there is a fixed amount, and we all agree to call this 1 meter. And then we can measure anything else in reference to this meter. So for example, the board is, so and the way I imagine doing this is by laying out meter sticks one at a time. And keeping track. So 1 meter, 2 meters, 3 meters, and about 3.4 meters. So the board is 3.4 of these. And so that's how we make our measurements. We have a quantity that we want to measure, and we define a system of units, really, but it's really a system of standardized measurements. And then we measure everything else relative to our system of standards. And that's how we measure things. Okay, so each quantity, different quantities will have different units or labels. So in this case, I said the word meter. But there could be other ones. So there are different, there are different protocols for how you would measure that. So you might use inches, or you might use feet, and you would have some sort of, basically the same idea, only you would use a different size stick. But that's how it would go. So we have units. So for length, people will talk about meters or inches or feet, or miles, or light years, or there are many other things we could do. There are all sorts of other ones. For time, it's really the same thing. We have, now a second is going to be our unit. It's defined in terms of some sort of frequency over which some atom oscillates. But it doesn't really matter. You can think about just an old traditional clock, and time has to do with, a second has to do with a second hand traveling so far around the face of a clock. And so we agree that that amount would be our standard, and then we compare every other measurement of time to that reference measurement, or that reference unit. So we'll have second. Other units would be minutes, hours, etc. Okay, so those are just different ways. And to make a measurement, you have to first have a unit and some sort of a protocol or method of comparison, and then you measure everything else in comparison to your basic unit. For mass, in the metric system, which I'll talk about in a minute, we have kilograms. And then there are also, in everyday language, people use something called a pound. That's actually a little tricky, because there's actually a concept of pound of force and a concept of pound of mass. And in general, they're different, but on Earth, when you're standing right here, they actually are very closely connected. So we'll come back to that later. But so I can have a pound of mass. I'm just going to call it LBM, a pound of mass. If I want a pound of force, I say LBF. And it actually turns out that the official way you should define mass in the English system is with a unit called a slug. And so I'm talking about bugs. It's an amount of mass. We're not gonna use this ever this semester, but that is the actual kind of basic unit of measurement in the English system. Okay, so we have all these units. Of course, by changing, you can measure one stick in terms of another stick. So that means you can measure inches in terms of meters, or feet in terms of meters, or meters in terms of feet. You can go back and forth. You can convert things. So there's no right or wrong, even though I joke about it. You can go back and forth between them. That being said, there are some sets which are more convenient. And for most of our applications in Physics 1, the metric system is the most convenient set of units because it's so easy to go back and forth between them. So sometimes I say, we use the metric system because we're civilized. And because it kind of is, it takes less to actually remember to make the conversions. Unfortunately, because there are barbarians around, you do have to know how to convert to the other units. So we'll go through that. So let's talk about how to go between, how to relate different units. So what I'm going to do is I'm going to, actually first, let's go through the metric system. And then we'll talk about making unit ratios and then doing unit conversions in general. The metric system. So the metric system is a series of, what you do is you always have a basic unit, and then you come up with a collection of other related units, which differ by factors of, well, always factors of 10. Typically, they differ by factors of 1,000, or for the common ones. So really with maybe one exception for us, that's what we will have. So I'm going to start with meters, because I think that's probably the most familiar. but then the idea works no matter what. So the idea would be you start with kind of the primal quantity, a meter, and then you can define other related units, which differ just by a rescaling, like a factor of 100 or a factor of 1,000 or 1,000, it can be bigger or smaller. And we indicate the fraction that you multiply by with the name through a series of prefixes. So I'll show you how it works. Okay? So we have a series of prefixes. Probably the biggest one we're going to need is mega. So prefixes, the factor they correspond to, and then we'll go through an example here. You can kind of see. So, I suppose the biggest one you might have heard of is we have hard drives. Computer hard drives are now in terabytes. Okay, tera is one of the prefixes. We have tera, T-E-R-R-A, and the abbreviation would be a capital T, and that is a factor of a trillion. So that's 10 to the 12. So that is a 1 with, that's 10 to the 12 is the factor that's associated with that. Then we have a billion, and that comes up with computers also, gigahertz. Okay, that means a gigahertz processor does a billion processes or operations per second. Cycles per second. Okay, so giga, and so I use G for that. That would be 10 to the 9. So they differ by a factor of 1,000, which is what happens for most of these units. Tera, giga, we have mega. And the symbol we use for that is capital M. That's 10 to the 6. And we have kilo, that would be 1,000. So that's a lowercase k. That's 10 to the 3. Those are the standard ones which are larger than 1. There are some other ones. You can have deca, so that would be just 10, the first power. But it's not standard, so we won't use it in this class. So then other prefixes that we will use are ones that refer to things less than 1. So we can have centa, and that is a lowercase c, and that's actually 100th. So it's 10 to the negative 2. That one's an oddball. These all differ by 3s. 12, 9, 6, 3. Those differ by factors of 10 to the 3. Centa is an oddball, but it's a convenient one for us, so we stick with it. And then we will have milla, or milli, M-I-L-L-I, and that is a lowercase m, and that is a 10 to the negative 3. That's 1,000. And the last one, and I'm almost out of space, but I'll squeeze it in here, is I have micro. The last one we will have, there are other ones. And that is actually a Greek letter mu. It looks like a blend of an M and a U. It's a mu. Don't say moo, we're not cows. Mu. And then that is a 10 to the negative 6. Okay, so how do we use these? This is just a list of, oh, I forgot my friends. Okay, so how do we use these to relate things? So what I'm going to do is combine these, and I'm going to use meters, just so it's a simple thing. So what I would do, this table of values, is I would say, for example, 1 kilometer, so 1 kilometer, so I'd write 1 km, kilometer, is the same as, I go over here and I look at my conversion factor, 10 to the 3 meters. 1 kilometer is 1,000 meters. That's how I use this table to get my answer. Let's try another one. Let's do centimeters. Maybe you remember, like a century. So that kind of is a hint. It has something to do with 100. So let's see how that works. So what I would have here is 1 centimeter equals, go over here to my table, 1 centimeter is 10 to the negative 2 times a meter. And that is 100th. So sometimes people will say that is 1 over 100 meters. 1 centimeter is 100th of a meter, and that's how you can use this list of prefixes. You can turn this around, because of course there are equivalent ways to write this. I prefer to think of it as 1 meter is 100 centimeters, and I don't have any fractions around. So that's fine. I've kind of flipped that fraction upside down by moving it to the other side. But it's the same idea, and it's the same information, just rewritten. Okay, so that is how the metric system works. So that allows us to define a whole series of different measurements, and you can relate them. You can go back and forth between. So let's kind of go through that process of converting things in a little bit more detail. So let's talk about unit ratios. Unit in math class means 1, but we also use it to indicate, choices of quantity that we make references back to. And we're gonna, I guess you could kind of think of this as an equivocation, kind of blending them all together. So a unit ratio is a ratio, it's a fraction that equals 1, but it is a special way of writing the number 1 that we can use to relate one choice of units to another. So for example, what you do to set up unit ratios is think of some equality. We'll use these since I have them on the board. Okay? And I know that 1 kilometer equals 1,000 meters. They're the same. It doesn't mean that 1 equals 1,000. It means that 1 kilometer equals 1,000 meters. If you don't put the labels there, if you don't put the words, it doesn't make sense. But with the words, it's okay. So if this equals this, they are exactly the same. Then if you divide them, the fraction has to be 1. So if I do 2 divided by 2, it's 1. 3 divided by 3, it's 1. Cat divided by cat, whatever it is, I don't know how you do that, but whatever it is, cat divided by cat would have to be 1, because a number divided by itself is 1. Okay? So that means I can say that 1 equals 1 kilometer divided by 10 to the 3 meters. This ratio, even though it doesn't look like 1, it is 1, because the numerator and denominator are the same. There's another unit ratio we can define, which is the reciprocal. They're the same, they're 1, and multiplying by 1 is the same as dividing by 1, so I can turn the fraction upside down. So that means I can also say 10 to the 3 meters divided by 1 kilometer is 1. These are called unit ratios. And anytime you have two amounts that are the same, you can form a unit ratio just by dividing them. And if they're the same, the ratio is 1. That's how that works. We're going to use these unit ratios to help us convert one quantity in one, measured in one set of units to another set of units by really just multiplying by these unit ratios. So, for example, see how I can do that. Let's imagine I had 10 centimeters. And I wanted to convert that to meters. 10 centimeters converted to meters. Well, what can I do here? Oh, incidentally, we can't add, we don't know how to add things unless they have the same units. So I don't really know how to add inches and feet. What I have to do is convert them to the same, and then I can add them. And I sure don't know how to add inches and pounds. That doesn't ever happen. You can multiply amounts with units, but you can't add them. That's an important thing to know. So I somehow want to start with this, and I want to use these ratios, or other ratios that I might form, to change centimeters into meters, let's say. Well, to do that, actually, I'm not going to use these. I'm going to use this one to form a unit ratio. So rather than using the top line, I'm going to use the bottom line for my unit ratio. So this unit ratio will be, well, I can divide, and I can either say 1 equals 100 centimeters divided by 1 meter, or I can say 1 meter divided by centimeters. Let me write those. So the goal is to convert this to meters. That's what I want. And my unit ratios that I can form using this fact are 1 equals 1 meter divided by 100 centimeters. Or I could also use 1 equals 100 centimeters divided by 1 meter. Okay. These are my two expressions for the unit ratio, and I want to use them to convert 10 centimeters to meters. And I just said, well, I'll go ahead and give you a hint. We don't want to add them. So what we're really allowed to do is multiply or divide, but multiply and divide. So if I were to multiply this expression, this amount, by one of these two unit conversion factors, one of them will produce an answer in meters. If you think about it with a little thought, the way I think of it is I want the bad stuff to cancel and I want the good stuff to survive. And so I start out with a centimeters upstairs. So that means the fraction or the ratio I need to multiply by should have centimeters downstairs so that it will divide out. I'll show you. And then if I've done it right, the thing I want is what will be left behind. So what I'm going to do is, because this was upstairs, this was in the numerator, then I want to multiply by the unit ratio with the bad stuff downstairs. So I'm going to choose this one, the unit ratio on the left. And I'm going to have 10 centimeters times, I multiply by the unit ratio. You might say, well, wait a minute, it's 10 centimeters, but if I multiply by something, I'm changing the answer. No, you're not, because we're multiplying by 1, and we can always do that for free without changing the answer. And that's the real reason why you can't add, because if you add the ratio to something, beyond, maybe I don't know how to do that with mixed units, but in adding it by 1 changes the answer. We want to keep the answer the same, so all we can do is multiply by 1. We're just trying to multiply by 1 in a clever way to have the effect of converting units. So I multiply by 1 meter divided by 100 centimeters. And look what happens. The units, centimeters, cancel with units, centimeters. You can just treat them like any other. They kind of, they work like numbers in that sense. They're just labels. And when you do that, I'm left with 10 divided by 100. So that's a tenth of a meter. And if you think about it, that makes sense, because if 100 centimeters is 1 meter, then 10 centimeters would be a tenth of a meter. So that makes sense. So unit conversions are accomplished by multiplying by combinations of unit ratios to take the units you start with and convert to units that you wish you had been given. Let's do a more complicated example. Using information. So the next one I'm going to use, I think I'll save this because that'll be useful, is let's say that I had 2 centimeters, and for some perverse reason, I decided that I would like to know how to convert 2 centimeters into kilometers. I don't know why, you know how it is, small town, not much to do. Let's do this. So we start with 2 centimeters, and we want to convert that to kilometers. So that's what we want to do. Well, so any one of these lines gives me a unit conversion from a quantity to meters. So these lines in this table allow me to convert things to meters. Or in particular, then I know conversions between meters and centimeters. And I know conversions between meters and kilometers, but I don't have, at least without some practice, I don't have a direct conversion from centimeters to kilometers. No big deal, we just do it in 2 steps. So we're going to multiply by 1 twice, and we're going to choose our representation of 1 so that the stuff we don't want goes away and the stuff that we do want survives. So the way we're going to do that is we're going to start with 2 centimeters, and we're going to multiply by 1, and I need to multiply by 1 in a way that makes centimeters disappear, and I can't get all the way to kilometers, but I could go to meters first, and then go from meters to kilometers and do it in 2 steps. So from centimeters to meters, well, I have that conversion. That's right here. So I can just say this, I form the unit ratio 1 meter divided by 100 centimeters. And if I think about it, that's going to cancel those. So now my answer is going to be in meters. That's the only thing that survived. But that's not my goal. My goal was kilometers. So I'm just going to multiply by 1 again. Just keep on going. And I want to start with meters now, and I want to get rid of those and end up with kilometers. So I want to say that's 1 kilometer divided by 1,000 meters. Okay. So I multiply by 1. I've done it twice. I'm allowed to do that. You can multiply by 1 as many times as you want without changing the amount. But I've done it in a clever way so that the bad stuff, quote, centimeters, goes away and kilometers survives. So what I'm left with is 2 times 10. Now I'm going to use scientific notation because it makes it easier to keep track of these things. Dividing by 100 is like 10 to the negative 2. Dividing by 1,000, 10 to the 3, that's like 10 to the negative 3. I'm going to multiply them, the exponents can add. So that's like 2 times 10 to the negative kilometers. So 2 centimeters are like, let's see, so that would be 200 thousandths. So 200 thousandths of a kilometer. Some insane amount. Okay, so hopefully that makes it clear how you would handle unit conversions and how you might have to have multiple steps to do that. The metric system is particularly nice because all these factors, these unit ratios, are just factors of 10, 100, 1,000, but simple things. Here in a minute, I'm going to tell you about inches and pounds and blah, blah, blah. And it's the same idea. It's just that you don't get nice factors of 10. The conversions are a little bit more complicated. Okay. So there are a list of numbers, or conversions that I'm going to give you. And I want you to know these at the level that I'm describing. And the reason I want you to memorize them, kind of really absorb these, is that way, these are going to be the conversions from everyday units to the metric system. And we will solve problems in the metric system. But sometimes, if you're not familiar with what the units mean, you don't have an intuition for them, it's hard to even know if your answers are reasonable. So if you know the conversion factors, you can have a pretty good idea if your results are reasonable. Also, when we solve problems together, there'll be a lot of times where we'll start with an everyday scenario, so I'll describe it using everyday terms, and then we'll just sort of quickly convert it to metric and then solve the problem. So anyway, so that's what I want to do. So useful conversions that you should know. We should all know that 1 inch is 2.54 centimeters. Hopefully that's familiar. Similarly, 12 inches would be 1 foot. 3 feet is 1 yard. Also, 1 mile is 5,280 feet. Now, it turns out to 2 digits of accuracy, so roughly, approximately, I can say that a mile is 1.6 kilometers. That's not exact. It's approximately true. So maybe I should put a squiggly equals. Okay, so that's approximately true. When we're solving problems in class, it's more than sufficient just to remember 1.6. There's no reason to carry out so many digits. When doing homework on sapling, you will need to use a more precise conversion. I think it's 1609. 1.609 is the more precise one. These are ones that you should know. Really, just every kind of scientifically trained person should know these length conversion factors. Other things that are useful to know is 1 kilogram is, again, approximately, not exactly this, but it's close, 2.2 pounds of mass. Sometimes people say 2.2 pounds, and again, you have to be careful. There's a pound of mass and a pound of force, and kilogram measures mass, so it has to be pounds of mass that it's really. Right. Another one that is useful to know is, this one will come up a lot because we have problems with velocities and speeds in metric system, and then you want to know what that means in everyday life. 1 meter per second is 2.24 miles per hour. And it turns out that is, again, that's approximate. That is approximately the same as 3.3 feet per second. Okay? That's a useful, kind of convenient conversion. And when you know it, I forgot one more. Approximately, we have that 1 yard is 0.91 meters. So a yard is a little bit smaller than a meter, about 10% less in round numbers. Or you can turn that around and say that 1 meter is, again, these are approximate, 1.1 yard. So if you know the number in meters, just add 10% to the numerical value. Excuse me, and that's the conversion to yards. And if you know the answer in yards, subtract 10%, and that'll get you to meters. Okay, so that's kind of good. These are very useful. We may have a few more through the semester. These are all equalities between different amounts, and you can use any one of these or all of them to make unit ratios, and therefore you can convert units with any of them and all of them. Okay. The last thing I want to do is talk about composite units, or just more complicated conversions. And it's really not hard. It's really what we did up there, where we had a two-step problem, only, you just have to kind of, maybe it's not so clear from the outset what you have to do. You have to kind of think about it. So we get composite units whenever, when you multiply various quantities. So for example, the one I'm going to do here is a volume. So if you want to know the volume of a cube, such and such big, it's the length times width times the height. Well, length has units of meters, width has units of meters, height has units of meters. So the natural metric unit of volume would be a meter times a meter times a meter. It'd be meters cubed. If you're doing chemistry, a meter cubed is a lot, right? Couldn't fit that in a test tube. So in chemistry, people oftentimes use centimeters cubed, which is, or an equal amount, which is called a milliliter. We won't use liters and milliliters much in this class. So for us, volume will be done in terms of meters cubed. But those are composite. They're built out of the basic set of units. So to do that, so the example I want to do is I want to convert a meter cubed into a centimeter cubed. So if I have a meter cubed, how many centimeter cubes would that be? Or more physically, if you think about a meter cubed, a meter's pretty close to a yard. So that's like a yard times a yard times a yard. Okay, so that's like half a refrigerator, the inside of it. Something like that. Okay, and a centimeter cubed, well, that's centimeter times a centimeter times a centimeter. It's like a sugar cube or something like that. So you could ask, well, how many sugar cubes could fit in half a refrigerator, assuming no air gaps and things like that? That's the kind of number we're talking about here. If you think about it, is it 10? Well, no, you can put more than 10 sugar cubes inside the refrigerator. What about 100? Let's think about that. Well, you could lay out, if a sugar cube is, if this is the kind of bottom of a sugar cube, you could do 100 as 10 by 10. Whatever, you get the idea. So 100 sugar cubes would fit in something like this. That easily fits inside this. So we're expecting, in fact, you can even stack this 100, 10 times deep. That'd be 1,000. So 1,000 would fit in something like the size of a basketball. So when we talk about how many centimeters cubed would fit in a meter cube, or how many sugar cubes would fit in half a refrigerator, we're looking at for a number that's big, much bigger than 100 or 1,000. It should be quite a bit. So let's go through that. How would we do that conversion? So we're going to start with 1 meter cubed, and we want to convert that to centimeters cubed. Sometimes people say cc, but I will try to always remember it centimeter cubed. So you have to think about what this means. And to do that, I would just go back to thinking about how we find the volume of a box. Length times width times height. So that means meter times meter times meter. So that would be, I could write this as 1 meter quantity cubed. So 1 meter cubed is the same as 1 meter cubed. And we've already, then, hopefully it's not too surprising, we've already seen how to convert a meter to a centimeter. And if you just do that for each one of these factors, you get the answer you want. So what we will do is multiply this by 100 centimeters divided by 1 meter. That won't work by itself because I've got meter 3 times here and I've only got meter once there. It won't work. It'll still have meters floating around. But if I do this 3 times, then I'm good. For every power of the unit that's here, you have to have a separate conversion factor. And that's it. So the answer is really going to be it's really 10 to the 6. 100 times 100 times 100 is 10 to the 6. It's 1,000,000 centimeters. It turns out in half a refrigerator, you can put 1,000,000 sugar cubes, assuming no gaps and things like that. So if you're looking for something to do on the weekend, and you have lots of sugar around your house, give it a try. I guess tell me how it goes. But don't charge me if it breaks your refrigerator. Okay. See you next time.